So we're going to get started with Unit 10, Day 1. Our first topic is chords and tangents. This is our circles unit. We're going to start out with pretty basic vocab for a circle. You might know all of these or most of them. So other things I'm looking for, notation is important in this unit. The first one is a circle. We know that a circle is a two-dimensional shape where all the points on the edge of the circle are the same distance from the center, so it's, even all the way around. The way that we notate a circle is kind of fancy. We use the center point. So the center point in this circle is C. So we would call this circle C. And then the next three parts that we're going to talk about are all different kinds of segments that we can see in a circle. Chord is the name of a segment. Again, a segment has endpoints, and its endpoints are just on the edge of the circle. So, for example, I have a chord here with endpoints on the edge of the circle, and we call that chord AB. And because it's a segment, we use segment notation. The next one is a radius. A radius is not a chord because it does not have both endpoints on the edge of the circle. It is just a segment that goes from the center to the edge. So a radius, for example, in this guy would be CF. Notice it only has one endpoint on the edge, one endpoint in the center. So that would be CF. And then if I put two radii, which is the plural of radius, back to back, I get a full diameter. And a diameter is technically considered a chord because it has one endpoint on one edge of the circle, one endpoint on the other edge of the circle. So we would call this diameter DE. Hopefully those terms are familiar to us. Yes, nothing crazy so far. Now we're going to get into a bunch of theorems. Okay, so these theorems have reasons, they have justifications. It's going to sound proofy when I say it to you. I'm not expecting you to memorize the proofiness. I'm just expecting you to be able to look at a diagram and recognize, hey, I know what I can fill in here, okay? So first theorem says, in the same circle or in congruent circles, two minor arcs are congruent if and only if their corresponding chords are congruent. So I'm going to kind of try to label hypotheses and conclusions here just so we can kind of see what is causing what. So this one says two minor arcs are congruent. So those are these minor arcs here and here. An arc is a portion of the curvy part of the edge of the circle. If and only if their corresponding chords are congruent. So these chords here and here are congruent, therefore the arcs are congruent. If you remember that if and only if part, I know it's been a minute since we talked about it, but if and only if means that it is true both ways. So I could either start with the chords or I could start with the arcs, and it works either way. Questions on that one? Okay, the next one says, if a diameter or a radius of a circle is perpendicular to a chord, then it bisects the chord and its arc. So here's my hypothesis. Diameter AB is perpendicular to chord XY. So I'm saying I know that these two pieces are perpendicular. They're forming a right angle. Then, conclusion, XZ is congruent to ZY. So that means that the two pieces of my chord are congruent. And the two pieces of my arcs are congruent. So XB here and BY here are congruent. Do we see hypothesis and conclusion? If I know that that diameter is perpendicular to the chord, then I know that that chord and its arc are split in half. Questions on that one? Okay, moving on to the next one. The perpendicular bisector of a chord is a diameter of a circle. So again, hypothesis, if AB is perpendicular bisector to chord XY. So AB is perpendicular and a bisector to XY. Then I can say AB is a diameter. That one's not used super often, but it is good to know that if I have a diameter, that if I have a perpendicular bisector, then I also have a diameter. I really like this one. This one says, in the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center. There's that if and only if part again, which means I can say this either way. It works both ways. So this says two chords are congruent. So here's my two chords, F, G, and H, J. And they are congruent if and only if they are equidistant from the center. That word equidistant means the same distance away from. When we talk about distance in this unit, we are always going to be thinking about making right angles. So maybe make a little note for yourself. Distance is perpendicular. That's how we get the shortest distance to anything, is by drawing a perpendicular line to it. So when I talk about distance in this circle, the distance from the center to those two chords is literally the perpendicular line to those chords. So if the chords are congruent, then their distances are the same, and vice versa. If their distances are the same, then the two chords are congruent. Questions on these first four theorems? Okay. Next is another vocab word. So the next vocab word that we're going to talk about is tangent. A tangent is a line in the same plane as a circle that intersects the circle in exactly one point, called the point of tangency. So this isn't like the tangent is going through my circle. If it goes through your circle, it's not a tangent. It literally like bounces off the outside of my circle. So this tangent right here, here's notation, it's a line. So this is like tangent AB, and to denote a line, we use the arrows on the top. And then that point that it is touching my circle, but then bouncing back off and going the same direction is called the point of tangency. So we call that point A, or just A, one capital letter for points. So kind of two definitions here. We have the tangent and the point of tangency. Okay, then I got two more theorems strictly for tangents. So let's flip it over to the next page. The first theorem for tangents is super important. It says that if I have a tangent, then it makes a right angle. It is perpendicular to a radius or a diameter of my circle. So here's my tangent. It's that line L that's on the bottom. So let's see. Let's do this hypothesis and conclusion. So it says line is tangent to a circle. So here's my line, tangent to my circle. It bounces off at that one point T. If and only if, meaning it goes both ways. And then it says it is perpendicular to a radius at the point of tangency. So that point of tangency T, we're going to form that perpendicular line. And that's going to help me. So not only do I know that if I have a tangent, then I must have a right angle, but also I can use this to prove that things are or aren't tangent. Because if I can't prove that I have a right angle, then I must not have a tangent. Any questions on that? And then the last one, this is kind of fun. This says if two segments from the same exterior point are tangent to a circle, then they are congruent. So again, hypothesis, two segments from the same exterior point are tangent to a circle. We're assuming these guys are tangent at these points A and C, and they come from this exterior point B. Then, by definition, or not definition, by this theorem, they are congruent. So these two pieces must be congruent. If you turn your paper over, it looks like a little guy with a party hat. So that's how I like to think about it. So this little guy with his party hat, here's his eyeballs and his nose and his face. Look at him, he's so happy because his party hat is congruent on either side. It's not wonky. Okay, good. Questions? Fantastic. All right, let's get into some examples. I have a lot of examples. I have this page and the next page, so we're going to fly through them a little bit here. First, the diameter of circle X is 22 units. The diameter of circle Y is 16 units and WZ equals 5. The importance of this unit in filling in your diagrams is so immense. You need to fill in your diagrams with whatever information you have, or you're going to be stuck looking at a picture for forever. So I know that WZ is 5. And then I get a little bit stuck because it tells me some information about diameters. And if you know about what a diameter looks like, neither one of these circles has a diameter drawn in it. So instead, what I'm going to need to do is transfer these into radii. So if the diameter of circle X, that's my bigger circle on the left, is 22, then the radius is going to be half of that diameter. The radius is 11 units. So I know that XZ here is 11. And then I also know that the diameter of circle Y, which is that circle on the right side there, is 16. So the radius is half of that. It's 8 units. And now my drawing is filled in. Now that it's filled in, it's much easier to see how I'm going to figure out the length of XY. I know that these pieces I can fill in just using a little bit of subtraction. So like if this whole thing is 8 and that little piece is 5, then this must be 3. Same thing over here, this must be 6. So I can like add pieces together. XY is a total of 14 units. Let's just say it's like 11 plus 3 equals 14. Okay, a bunch of different ways we could have filled that in and done it, but 14 units. Anybody have questions on that? Okay, they love to give you these word problems where we do not have a picture drawn. So we are going to draw our little watermark from this jewelry company, which is a circle. I don't know what their watermark is, but it's got a circle in it. There you go. Okay, it says the watermark is a chord located 0.7 centimeters from the center of a circular ring. So there's my circular ring with a center that has a 2.5 centimeter radius. To the nearest tenth, what is the length of the chord? I've got a lot to figure out here, and I'm imagining something that doesn't exist. When we get a problem like this, we're going to put our chord anywhere we want to. We're going to put our radius anywhere we want to, but we're going to put them in places that are purposeful and that help us solve this circle. So I'm going to draw a chord, any chord. Here's my chord. I need to say that that chord is 0.7 centimeters from the center of my circular ring. If I am talking about distance, remember what I told you when I was talking about definitions, distance is represented by perpendicular lines. So if I want to draw the distance from the center to that chord, I'm going to start at the center and draw a perpendicular line out to that chord. That distance is 0.7 centimeters. Everybody with me? Then it says it has a radius of 2.5 centimeters. Where am I going to draw that radius that helps me solve this circle? I don't just want to put it anywhere. I need to put it in a place that's going to help me figure out the length of this chord. Anybody have an idea? Dahlia?
Did you connect it to like one of the ends of the chord?
That's exactly what we're going to do. In circles, we use triangles to help us solve these parts. Triangles and circles go hand in hand. That's why we do these two units next to each other. So I'm going to go ahead and draw in my radius right there to form a circle. And that radius is 2.5 centimeters long. Then the question is asking me, what is the length of my chord? So I need to figure out this whole thing. And we're going to have to use a little bit of a theorem here that says if I have a perpendicular like radius to that chord, which is that red line right there, it's perpendicular, then it's splitting that chord into two congruent pieces. So these two pieces are equal. Let's call them x and x. I'm solving for x. I'm going to use Pythagorean theorem. I'm not going to make it difficult here. We're literally just doing x squared plus 0.7 squared equals 2.5 squared. I mean, I'll let you do the math on that. I believe we end up with 2.4 as x. And then to get the length of my chord, I got to take that and multiply it by 2. So 2 times 2.4 is 4.8. centimeters. Let me put centimeters in there. Okay, so you will have problems like this where you have to imagine your own circle, but you're going to place things. Well, the first thing that you place is probably just wherever you feel like putting it. When you put in a radius, you got to put that radius in a place that makes sense for solving with triangles. Okay, so let's get into some more theorems. So this theorem, pretty straightforward. It says if I have two arcs congruent, this is the very first one we talked about, by the way. If I have two arcs congruent, then their two chords are congruent. So we see the two arcs that are congruent here and here. That means these two chords must be congruent. So I can set up x squared minus 5x equals 24. We're going to be doing this a lot with these circles. It's just setting two pieces equal. And in order to solve this, I do have to factor it. So I'm going to subtract that 24 and factor this. I believe my factors are x minus 8 and x plus 3. So I get two answers. 8 and negative 3. Everybody with me right now? Now pay attention to this part because I'm going to see this a lot and you're going to make this mistake. When I get two answers, because I factored, I need to check them. I cannot just cross them off all willy-nilly if I have a negative, and I can't just leave both of them. I have to check. So I'm going to plug in my negative value, so that negative 3 squared minus 5 times negative 3. And what do I get? Well, if you do this math, you get 9 plus 15, and that's a positive 24. So that works perfectly fine, right? So what I don't want to see is us crossing things off without checking. Don't cross off values without checking. That's my note of warning to you. So sometimes that negative 3 doesn't work. Sometimes we get a negative number and then we know we can't have a negative lengths. But sometimes that negative does end up working. So you gotta pay close attention. Everybody with me on that? All right. Same theorem for number 4. If I have two chords congruent, so these are my two congruent chords, then I know their two arcs must also be congruent. So if that one is x, this one is also x. What do we know about the arc measures of a circle? What do they add up to? You go around a whole circle? Yeah. Yeah, they add up to 360. So I am going to do 360 equals x plus 90. Or I believe this is 270 equals 2x. Or 135 degrees is my x value. Questions on those ones? Flip it over. We got a couple more examples to get through. I know this is a lot of examples. Okay. All right, and number 5. KL is a radius of circle K. Determine whether LM is tangent to K. So they love these types of problems where it says determine whether something is tangent. By our theorem, which is our first theorem about tangents, this one right here, we know that something is tangent if and only if it is perpendicular to a radius at the point of tangency. So what I am trying to figure out to know whether this LM is tangent or not is whether this is a right angle or not. Well, how do I determine if something is a right angle? I'm going to go back to my stuff from Unit 9 vocab, and I'm going to figure out, are these three numbers a Pythagorean triple? Do they form a right triangle? So I'm going to go ahead and set these values up. 20 squared plus 21 squared. I want to know if that equals 29 squared, and I believe both sides do equal 841. So then we could say, yes, LM is tangent because those two pieces are congruent. Questions on that? Okay. So that's when it says determine whether this is tangent or whether this is a right angle or something like that, okay? For the rest of these, let me figure that out. Yes. For the rest of these, for 6 through 10, we are now going to assume tangents are tangents. So maybe make a little note. For 6 through 10, we're now assuming tangents are tangent. I believe in your math lab it says that same thing, like assume that these things are tangent. I'm just telling you right now so we don't get confused on why we're getting right angles and stuff like that. Let me put numbers 6 through 10. Okay, so number 6. I know that line ST that looks like it's tangent is tangent. So because it's tangent, I'm going to start right away by putting a right angle in there. My goal is always to get triangles to solve, especially those right triangles. So with that triangle in mind, I'm going to figure out how do I get the remaining pieces here. How do I figure out the length of TR? Well, I need to first fill in. They love these. They love to do these. If this radius is 15, I also see another radius in my circle that is also 15. We see this RU right here. Any radius in a circle is the same as any other radius in the same circle. So if the radius is 15, no matter where I put that radius, it's also 15. Think about the setup here. Think about how I would do this in Pythagorean theorem. I would have like 36 squared plus 15 squared plus x plus 15 squared, which I would get a crazy thing that I need to factor. Does anybody really want to factor that? I don't. So instead, make this easy for yourself. This is a little trick, a little hack. I'm going to call this entire thing y. I'm going to figure out what the length of that hypotenuse is before I even worry about finding x, because look how much easier it makes this problem. So 15 squared plus 36 squared equals y squared. We can literally do that whole thing in my calculator. 15 squared plus 36 squared, square root it. I believe we get something like 39. And then rather than factoring to find our x, now all I have to do is say, well, y equals 15 plus x, and y is 39. Oops, 15 plus x. So x then must be 24. Look how nice and easy that was for us. Don't do more work than you have to do. I mean, could you figure this out by factoring? Yes, but I think you're factoring like crazy hundreds of numbers. Let's take a look at this one over here. Number 7, it says find the value of x. Again, we're going to assume that line on the bottom is tangent, not those lines on the side, not the legs. Legs are not tangent because they're going into the circle. Tangents bounce off of the circle. But this guy is tangent, which means if I draw a radius to that point of tangency, I'm going to get a right angle because I'm assuming that that's tangent. And then again, here's that same idea. If I have a radius in my circle, which here's a radius from the center to the outside, and that's 30, then any radius in this circle must be 30. There we go. So this is also 30 right here. Again, do I want to set up 40 squared plus 30 squared equals 30 plus x squared? Not necessarily. So I'm going to make this easy for myself. I'm going to call that whole thing y. So 40 squared plus 30 squared equals y squared. We're going to simplify and square root. Y equals 50 here. So then if that whole thing y is 50, then 50 equals x plus 30, and x equals 20. Look at how much easier that is than trying to factor this. Okay, questions on those? Okay, look at number 8. A little bit different here. In number 8, I can't use my old trick because if I put a y on that hypotenuse, I'd have a y and an x. So unfortunately, I'm stuck with it. I gotta just work it out. So I'm going to, again, set up my Pythagorean theorem. Here's my tangent, dw, by the way. I know that's a right angle. So I'm going to set up x squared plus 24 squared equals x plus 16 squared. That's the whole length of this hypotenuse, x plus 16. I'm going to put an angry face note up here because I don't want to see anybody saying x squared plus 16 squared here. We actually have to split this and FOIL it. So this is x squared plus 32x plus 256. And then let's drop down this right side. I believe this is x squared. Oh gosh, x squared plus 576. Okay, everybody with me? And I'm like, oh, darn it, I have to factor. But actually, when I move those x squareds to the other side, do we see how they cancel out? If I subtract x squared from both sides, hey, look at that. They cancel. So I'm left with 576 equals 32x plus 256, which is much easier. It's 320 equals 32x, and that equals 10. So look at that. Again, we've once again avoided factoring. Isn't that nice? All right. 2 more. I love these problems. These are my party hat problems. Number 9, it says AC and BC are tangent to circle Z. Find the value of X. Okay, if my guy's wearing his little party hat, then I know that both sides of the party hat are congruent because he's happy about his party hat being equal. So these 2 little pieces are congruent. I'm literally going to set them equal. We do this so often in this unit. Set those 2 pieces equal. Do a little bit of solving. X equals 5. That's literally it for that problem. Good on that? Now we're going to use that value, and we're going to look at something that we see a lot. This looks scary. It's like, oh my gosh, there's a circle inside of a triangle. That's nuts. It's not that bad, okay? This is like a guy wearing 3 party hats, okay? He's just an overachiever. He's wearing 3 different party hats. Each piece of the party hat is going to be congruent. So for this little party hat on the top, these 2 pieces are equal. 2x plus 2 equals 3x minus 3, which I believe, again, we're going to get x equals 5. Over here, this party hat is also congruent. 34 minus 2z equals z plus 4. So this is 30 equals 3z, or z equals 10. And then over here, I've got 5y minus 2 equals 3y plus 2, because these 2 pieces of his party hat are the same. I missed some marks over here. So this is what? 2y equals 4? Or y equals 2? And then I'm almost done, because I got to read my problem. It says find the perimeter of this triangle. So I actually have to figure out what these values are. I am going to save myself some time. I'm not going to plug this in for every single piece. I just need to plug it in for one of each side of the party hat. So I'm going to do 2 times 5 plus 2. Oops, that was terrible. Sure. Which tells me that this side is 12, so this side is also 12. I'm going to do 10 plus 4. So this side is 14, and this side is also 14. And then I'm going to do 3 times 2 plus 2, which tells me this is 8, and this is also 8. The perimeter, we're going to go all the way around. 12 plus 12 plus 14 plus 14 plus 8 plus 8. The perimeter is 68 units. Okay. We did it. Any questions?